This is the notes for 7-6, which is about similarity transformations. So we actually skipped this lesson. It was 4-7, so we didn't talk about the congruence transformations. So we're talking about similarity transformations. So we need to talk about what a transformation is. So a transformation is an operation that maps an original figure, which is called the pre-image, onto a new figure called the image. So when I say maps, you might have heard that when you did functions and not functions. So the input maps to the output, so it goes to or goes with. So it's kind of like talking about corresponding parts. So a transformation can change the position, size, or shape of a figure. So let's go over some vocab that was in there that in transformation. So pre-image is the original figure in a transformation. So pre-image is before, okay, before. And then we have the image, which is the resulting figure after a transformation. The resulting figure in a transformation. So it a lot of times we get confused because we think image is the original. No, pre-image is the original, and image is you can think of it like post-image, but we just call it the image. So think of it like you see a computer an image of you. It's not actually you, it's just a picture of you. So you're the original, you're the pre-image, and the image is like a picture of you. Okay, so the next word is dilation. So when you think of the word dilation, you think of things like getting your eyes dilated at the eye doctor. And a lot of people will pronounce this dilation. There's no A after the I. It's dilation. You get your eyes dilated, not dilated. And so you think about getting your eyes dilated at the eye doctor. So that's when your pupil, so if this is your eye and say this is your pupil, so I'll draw, there's your eyeball. It's a really great drawing. And then when you get them dilated, that's when your pupil becomes a lot bigger. And so when your pupil becomes bigger, and you guys maybe have done this when you close your eyes or you turn off the lights for a while and maybe like count to 10 and then then you turn on the lights and you watch somebody else's eyes and your pupils get smaller quickly because when your pupil is larger, it's letting in more light. So when it's dark, our pupils are more dilated because they're trying to absorb as much light as they can so we can see better in the dark. And then so when there's light, if it's too bright of light, that's when your pupils go smaller because only you can only take a certain amount of light into your pupils. So fun little information there. So dilation is just a similar figure. So it got bigger, but the ratio, that it's still going to be a similar figure. So all circles are similar. But that's what we think about when we think about dilation. So it's the same idea here when we talk about dilations. So it's simply a transformation that enlarges or reduces the original figure proportionally. So it's a type of similarity transformation. So again, we didn't actually do congruence transformations, but congruence transformations is just like taking a figure and just rotating it or flipping it over the y-axis or moving it around. So it doesn't change its size or shape. It's just changing its position, orientation, or position or orientation. All right, so a similarity transformation is a transformation that results in a similar figure, so like dilation. Okay, so something really important here is the scale factor of a dilation. So we've talked about scale factors before, but they're a little different with dilation, so you have to pay attention here. The ratio, so the definition is the ratio of the length of the image, that's the resulting figure, to a corresponding length on the pre-image. So notice this is always, always, always in that order. So the scale factor of a dilation is always image to pre-image. So I want you to write this over here on the side. It's always image to pre-image. Now before, remember, it depended which way you were going to say it. Like if you said whichever figure first, that always went in the numerator. No matter what, the image, which is the resulting figure, will always go on top. So really, scale factors of dilations make more sense to us because if you think about it, if you're thinking about making like a scale model, so say you're making a scale model of a car. So you've got the big car, right? I'm not going to attempt to draw a car, but say this is a car. And you find the scale model, you're going to make something that's proportional to it. And, it's going to be maybe 1/8 of the size. So it makes sense that the image is 1/8 of the original. Before, it's usually turned around to go from here to here. Since this one was listed first, the bigger one would be on top, so it'd be 8-1. But when we're talking about dilation, it'd be 1/8 because the resulting figure is smaller than the original figure. And then we can also do things where we blow them up. So think about a picture. So this will actually work with that picture I just drew. If you have a 4x6 picture, and you're trying to blow it up, you blow it up to 8x12, then you doubled the size of the picture. It's 200%. So that makes sense with a dilation because before, if we said this to that, it would be like, so if this was 4x6 and this was 8x12, if we went from this to that, it would be 4-8, which is a half. But when we look at it as image and pre-image here in a dilation, it will always be the image, which in this case is going to be the blown up picture, to the pre-image. So it'd be 8-4, which is 2, which makes more sense in my brain because it's double the size. The end result is double the size of the original. So to me, it makes a little more sense to look at scale factors of dilations. So let's go back up to this paragraph here. So the scale factor of a dilation is represented with the letter K. And so this is specific to scale factors of dilations. So to perform a dilation, which we're not going to do so much of in this chapter, we will later, you need a point of dilation. It's often the origin. And so I'm going to talk more about that later. But not only do you need a point of dilation, but you also need the scale factor. And again, we'll deal with more of that in a later chapter. So there's two different types of dilations. You have an enlargement, so that is an image that is bigger than the original figure, or larger. And a reduction is an image that is smaller than the original figure. So because the scale factor of a dilation is always written as what to what? Image to pre-image. So the resulting image is always first, then to the pre-image. It results in the following. So if it's image to pre-image, if k is greater than 1, that means that, in our fraction, that the length on the image is bigger than the length on the pre-image. So that means the image, the resulting figure, is bigger than this, so it's an enlargement. So if k is greater than 1, it's an enlargement. If k is between 0 and 1, so notice I'm restricting it to between 0 and 1 and not just less than 1, because if k is less than 1, then it would flip the figure over. If we're looking in the coordinate plane, it flips the figure over an axis as well. So we're not considering negative k values. So if k is between 0 and 1, so it's going to be like a fraction or decimal, not greater than 1, then that's going to be a reduction because that meant that the numerator, the length in the image, was smaller than the length in the pre-image. So a number divided by a number that's bigger than it will always result in something between 0 and 1. So k greater than 1 is an enlargement. K between 0 and 1 is a reduction. Now, why k not equal to 1? Well, if k is equal to 1, then obviously it's the same exact figure, so that would be a congruent figure. So when determining if a dilation is an enlargement or reduction, we don't consider negative k values, and I just talked about that. So how do we find k? What if we're given a dilation and we're trying to find k? Well, you're going to take the length of a side in the image, so I want you to underline or box or circle or something, that the image divided by the corresponding length in the pre-image, or side in the pre-image, length of the side. And I want you to note, there is a shortcut. Oops, a shortcut. That's supposed to say shortcut. There is a shortcut. However, you can only do it if the point of dilation is the origin. So I'm going to talk about that in one of the problems coming up. Do not assume that's going to be true, because it's not always true. So you can't do the shortcut, so you're going to get a bunch of stuff wrong. So just don't do it. All right, in some of our examples, we're going to have to verify that something is a similarity transformation. So if we have triangles, we can prove that the two similars are figure using SSS similarity, SAS similarity, or AAA similarity. And for all other polygons, you must show that, look, every corresponding angle is congruent, and all corresponding sides form proportions. Not just one. All form proportion. All corresponding angles are congruent. So it's a little work, but we're mostly doing quadrilaterals, if not triangles. Okay, let's move on to the next page and do some examples. Okay, this page, determine whether the dilation from figure A to figure B, so it's telling you figure A to figure B. So figure A is the pre-image, and figure B is the image. So you have to pay careful attention to that. Is an enlargement or a reduction. Then find the scale factor of the dilation. So here we've got a nice little picture here. So all we need to do is pick a side length and then two corresponding side lengths and see what if it's an enlargement or reduction and find the scale factor. So I'm telling you it's a dilation. I am telling you it's a dilation. So we don't need to confirm that it's similar by SAS or whatever, or having all four sides, that kind of stuff. We don't need to do that, because I'm telling you it's already a dilation. Just figure out the scale factor and whether it's an enlargement or a reduction. So you can visually see the answer to this question. If A is the pre-image, what we started with, so A is this triangle, and B is what we ended with, it's obviously a reduction because it got smaller. You would also figure it out it's a reduction once you found that K is between 0 and 1. Okay, so to do this, we have to pick a pair of corresponding sides. Guys, pick the easiest one. Right here, this length, we can count 1, 2, 3, 4, is 4 units long. And right here, from here to here, we can see that that's 2 units. Okay, so we need to do image to pre-image. So the length of the side in the image is 2, and the length in the side of the pre-image is 4, which reduces to 1/2. So we're going to say K, or the scale factor, is equal to 1/2. Because that makes sense, and it makes sense because we can see that B is smaller than A, so we can say B is half of A. So that's your scale factor, is 1/2, and we can see that it's a reduction. Now, I told you there's a shortcut. This only works if one of the vertices on your figures is the origin. So because that's true, you can get away with actually looking at the coordinates of these points. So you can say, oh, the coordinates of this point right here, the coordinate is 2.5, 1. The coordinates of this point, which is the corresponding point, is 5, 2. And then you can do, again, the image divided by the pre-image. So the the image is x divided by the pre-image is x. And again, you get a half. And then if you do it with the y's too, it needs to be the same. So 1 divided by 2, that's a half. But again, you can only do this in special cases, very, very special cases, which is when one of the vertices is the origin, which means it's often the point of dilation. So it has to be the origin in both of the figures. So the corresponding point, if we're looking at figure A, it has this point, and the corresponding point in figure B is the same point. So that has to be true. So not only does the origin have to be on one of the figures, it actually has to be in both of the figures and be a corresponding point to itself. So this point corresponds to itself, and that means it's the point of dilation as well. So you can get away with that shortcut only on those problems. So let's look at the next one. Oh, look, I can get away with a shortcut because I've got this corresponding point, which is this point 0, 0, which corresponds with itself. So in both of the figures, A and B, we have that point 0, 0, and it corresponds with itself. But for good practice, we're not going to do that shortcut because it doesn't always work. So this one's actually super simple because, again, we're just counting. So from A to B, so let's talk about reduction or enlargement. Here's A, what we started with. Now here's B. Obviously, it's an enlargement. And then, so we're going to find the length for A is 2. And the length for its for that side of the parallelogram A. And the corresponding side is 6 for the figure B. Now, notice we're not counting, you don't count negatives. It's a length, so it's not negative. Even though this is 0 to negative 6, the distance is 6. So remember, we always do image to pre-image. So that is equal to 6 over 2, which is 3. And it makes sense because k is greater than 1, which means it's an enlargement, which we already knew that because it's obvious that it's an enlargement. So it's an enlargement, and k is equal to 3, and that's our scale factor. All right, let's go on to the next one. Okay, so example 2 says graph the original figure and its dilated image. Then verify, this is where we have to verify. Verify the dilation is a similarity transformation. So again, use one of the similarity postulates. Okay, let's go ahead and graph this. I'm going to graph it. I want you to graph it. Pause and graph it yourself. I'm going to graph it so I don't take too much time in the video. There's the first figure. Make sure you're labeling those vertices. And there's the second figure. So notice they do share that point A. And so this is going to be one of those situations where the origin is not the center of dilation. So we can't use that quick little trick like we could have in the first example. So we need to confirm that this is actually a dilation. So we need to look at these two triangles. So one thing I forgot to mention was that which one's a pre-image, which one's the image. So whichever one is listed first is the pre-image. So that's going to play the role of pre-image, and this is the role of the image. And so in order to prove that these two form a similarity transformation, since they're triangles, we can look at one of those theorems, SSS similarity or SAS similarity or AA similarity postulate. The easiest one to use, well, okay, maybe there's an easier one. You probably see the easier one, but we're going to do the one with SAS. So I can obviously see that angle A is shared between them. So I can say angle A is congruent to angle A. And so that's just the reflexive property. So the corresponding angle is equal to congruent to itself. So now we just need to show that the sides surrounding this angle form a proportion. So that means we need to show that this leg is to this leg as this leg is to this leg. Now we're going to do it and also look at the scale factor. So we're going to do the image to the pre-image when we set this up. And it'll be more helpful when I do some simplification. So I want to make sure that AD, you want to show that AD is to AB as AE is to AC. So we want to show that this proportion is true. So we need to figure out all of those lengths. So looking at your triangle, you should see that there's a couple that are really easy to find. AC and AE we can count because they're vertical lines. So I'm just going to go ahead and get those out of the way. So we can see that AE is equal to 1, 2, 3, 4, 5, 6, 7, 8. And we can see that AC is just equal to 2. And now we need to find AD and AB. So to do that, we're going to use Pythagorean theorem. So this is actually going to be really easy for us to do. So all you need to do is draw a right triangle from the two endpoints. So to find AD, we're going to make a right triangle with AD being the hypotenuse. So I just need to draw like this and like this. And then we just need to count the side lengths. So this is 1, 2, 3, 4, and this is 1, 2, 3, 4, 5, 6, 7, 8. So it's 4 by 8 there, and so that's our right triangle. And so to figure out this hypotenuse AD, we know the hypotenuse squared, AD squared, is equal to 4 squared plus 8 squared, each of the sum of the legs squared. And we just solve it. So 4 squared is 16, 8 squared is 64, and 16 plus 64 is 80, is equal to AD squared. So to find AD, we square root both sides. So we get AD is equal to the square root of 80. We're just going to leave it like that for now. We're going to do the same thing to find out AB. So I'm just going to draw a little right triangle here. Then I can count. We've got 1 and 2. So AB squared, because that's a hypotenuse squared, is equal to 1 squared plus 2 squared, because that's the sum of each leg squared. So let's solve that quickly. 1 squared is 1, 2 squared is 4, and so that's 5, but that's equal to AB squared. So if we square root both sides, AB is equal to the square root of 5. Okay, let's see if our proportion is true. So we're just going to plug in our values. So instead of AD, we're going to substitute in square root of 80. So is square root of 80 to AB, which is square root of 5, is that really equal to AE to AC, which is 8 to 2? Is that really true? And looking at it on the surface, you really don't know. So I know, but I don't know if you guys know. So let's make sure it's right. I'll show you two different ways. So let's do cross products. So 2 times the square root of 80, is that really the same thing as 8 times the square root of 5? If you plug them both in on the calculator, you will get the exact same irrational number. So I'm using an equal sign here because these two, oops, there's 3 8s. Because these two numbers are exactly equal, but like this is an approximation of this, and this is an approximation of this, but the approximations are equal. So it actually does work. The other way I'm going to show you how to do it is simplifying. So when you have the square root of something divided by the square root of something else, it's equal to the square root of the quotient. So the quotient, the division of two numbers under a square root, is equivalent to the square root of the quotient of the radicand. And the radicand means the number under the square root. And that also works for products too. I've shown you this before. The square root of AB is equal to the square root of A times the square root of B. So this only works for multiplication and division, not for addition and subtraction. So that means I can take this fraction right here and reduce it. So I can change square root of 80 divided by square root of 5 into the square root of 80 over 5. And I know that I'm going to go ahead and change this into 4 because I know that's equal to 4. Then let's keep simplifying here. What's 80 divided by 5? It's 16. And then what's the square root of 16? It's 4. So it works. And you can also just plug in on the calculator, like do this. Square root of 80 divided by square root of 5. And you'll see that that's equal to 4. So you didn't have to do this. But this is stuff we're going to study in chapter 8. All right, let's do a few more examples here. To the next page. Example 3, photocopying. A photocopy of a receipt is 1.5 inches wide and 4 inches long. By what percent should the receipt be enlarged so that the image is 2 times the original? So when you're doing twice the original, so that's going to be, if you do that, we can just go ahead and figure out the dimensions. You're just going to double them each. So the enlarged image is just going to be double that. So it's going to be 1.5 times 2 is 3 inches by 4 times 2 is 8. So 3 by 8. And so if we look at, image versus pre-image, you're going to get 2 because the length in the image, let's say for the second dimension here, is 8 over the length of the pre-image, corresponding length in the pre-image is 4, that's equal to 2. And we were already told that. So what percent is that? It's 200%. So we look at this as percent, there's your decimal. So it's a 200% enlargement. Doubling something is 200%. Moving right along in the theater, and yes, theater can be spelled that way. It can be spelled either way with E-R or R-E. Adriana wants to create a dilated image of her ticket stub using the copier. The dilated image is 1.5 centimeters wide by 1.9 centimeters long. The original ticket stub was 5 by 6.4. What percent, so look at the question, did Adriana use to dilate the original image? Okay, so the dilated image is this. So we need to do image to pre-image. So we can just take one of the dimensions. So we can do the smaller dimension or the bigger. I think we should do the smaller. So the dimension in the image is 1.5 centimeters to the corresponding dimension in the original ticket stub, okay, that's your pre-image, was 5. So it's 1.5 to 5. And so we just divide that and you get 3/10, or you can just leave that as 0.3. So that would be our scale factor, which means it's a reduction, which makes sense because we were looking for, we had a result that was actually smaller than what she had. And so it's actually a reduction here. So what percent did she use to dilate the original image? Well, what's 0.3 as a percent? It is 30%. So this one was a reduction. One more example and then we're done. So it's similar to what we did on the previous page. Graph the original figure and dilated image, then verify the dilation as a similarity transformation. So I've got the original and the image. So remember, original means pre-image. So I'm going to go ahead and pause and graph. There's my pre-image, and notice that my image does share a point. That point is R. And notice I'm not going to color over this piece. I'm putting the smaller one over top. So here's my image and here's my pre-image. So we can see here's pre-image, image, so this is an enlargement. So our our scale factor should be greater than 1. And we're actually just trying to verify its dilation. So we have to show, since it's two quadrilaterals, you have to show that every pair of corresponding angles is congruent, and you have to show that corresponding side lengths form a proportion. So we can obviously see they're both rectangles, so all we need to state is all angles are right angles. So all congruent. So we can say that angle P, we do need to list them out. Angle P is congruent to angle W. Angle Q is congruent to angle X. And this is important, the order which you put it, because we can technically do it a couple different ways, but we're just going to assume the orientation is the same. So upper left, upper left, upper right, upper right. So angle Q is congruent to angle X, and no, we don't need to name any of them with 3 letters here. Angle Y is congruent to angle R, and angle S is congruent. I'm sorry. I actually want to say this in a different order here because I was going in the first image. So angle R is congruent to angle Y, and then angle S is congruent to angle R. So notice that angle R is the lower left for the image, but it's the lower right for the pre-image. So R corresponds with Y, but then R corresponds with S because this R is playing a role in each of the figures. All right, so there's our corresponding angles congruent. Now we just have to show that the proportion holds true. So we need to show that PQ, I'm just going to do all the numerators here, PQ, QR, RS, and PS. And then what corresponds with PQ? WX, with QR, XY, with RS, YR, be careful here, Y and then R, because we went here to here, here to here. And then PS is here to here, so it's WR. So we need to make sure that this proportion holds true. But guess what's so nice about this? We can count. PS is 1. So is QR. And PQ is 2. And RS is also 2. We can count. And then WX I can see is 1, 2, 3, 4. XY is 2, I can obviously see. YR is also 4. And then WR is also 2. So look, these are all equal to 1/2. So we just showed that all the corresponding side lengths form a proportion. So I know that these two figures are similar by the definition of similar polygons. So definition of similar polygons. So you can only say that if you show the definition of similar polygons, which shows all corresponding angles congruent, and it shows all the corresponding side lengths form a proportion. And that's it. So we can be done. Now, remember, you got to go show the sub that you completed the notes. Now work on homework quietly.